In a lottery game, a player picks 6 numbers from 1 to 21. If the player matches all 6 numbers, they win $40,000. Otherwise, they lose $1. What is the expected value of this game? At first glance, this problem seems pretty simple. But on further inspection, we notice that there's a little bit of complicated counting that's going on. So let's get started. When we talk about expected value, remember, what we're talking about is the wins and losses and the probability that those things occur. So I write down the expected value equation, which is we're going to take the probability of a win occurring times the win amount. And then we also have to go into consideration the probability of a loss occurring times the loss amount that occurs. That's really how we get our expected value. Now the probability of winning, that's the complicated part. We know what the win amount is. If a player matches all 6 numbers in this game, they win $40,000. The probability of loss, well, again, that's something complicated that we're going to have to figure out. And we do know the loss amount. That is a loss of $1 each time the game is played. So our basic setup really comes down to us determining the probability of wins and the probability of losing at this game. Before we take a look at how to get the probability of wins and losses, there's a couple assumptions being made in this problem that we have to talk about. The lottery game is described to be a player picking 6 numbers from 1 to 21. One way to think about it is to think of a bowl or a hat, right? A collection. And then in that hat or bowl, there are 21 different slips of paper, okay? And on those slips of paper, there are different numbers ranging from 1 to 21. So this is one way to think about it. And those numbers are in the bowl, right? And when you win, what happens is you take 6 numbers or 6 pieces of paper out of that bowl, and a win is categorized by having 6 numbers that match the win. For example, let's say a win would be 6, 5, 4, 3, 2, 1. Well, that will classify as a win in the same way that 1, 2, 3, 4, 5, 6 will classify as a win. As long as you have a combination of 6 of the numbers needed to win the game, you're going to win. We can summarize this idea that's inherent in this game, but not directly stated, that there's going to be non-replacement. If you've heard of those terms before, non-replacement means once we take a piece of paper out of that bowl, it stays out, right? So we have this idea of non-replacement. And we also have the idea that we have to keep in the back of our minds that it's all about the specific numbers. And so the order itself, it doesn't matter if we pick this 6 first or the 6 last, or maybe we put a 6 in the middle, right? If the winning combination consists of the numbers 1, 2, 3, 4, 5, 6, then the order itself or the different way that it's chosen also doesn't matter out of that. So each of these different ways are going to count as a win, okay? So each of these orders and many more, right, would count as a win. What's important is that we have those 6 specific values. All right, so once we get just the basic understanding of the game out of the way, then we can start talking about how to get the probability of a win occurring and a loss. We're going to put our thinking caps on. Let's talk about the probability of a win occurring. Now, in the general sense, we understand that the probability that a win occurs is the number of ways to win at this game divided by the total number of possibilities. Let's break each of those up into 2 separate categories then. All right, I'm going to start with the possible total possibilities. So I'm going to start with my denominator first. So in my denominator, I am thinking, this is what I'm thinking. I have 6 different slips of paper. Okay, this is what my head's saying. And I have to do one after the other, after the other, after the other. So I'm going to be multiplying down the occurrences. In other words, I have to count how many different total possible ways, how many different total possible combinations are there if I take 6 pieces of paper out of a bowl of 21. Well, we haven't talked at all about permutations or combinations, but we can understand this kind of counting idea that I'm going to describe. When we pick that first slip of paper out of a bowl, how many different numbers could that piece of paper be? Well, there are 21 different choices, right? That first slip of paper could be a number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to 21, right? So there are 21 different numbers that first slip of paper can be when I pull it out of that jar. All right, so I've pulled that first slip of paper out. What happens to the next slip that I take out? Remember, we're not replacing. There's no replacement. So now when I go to pick this second slip of paper, how many different numbers are left over for me to choose from? There are 20 different numbers left over to choose from. Does that make sense? Because now there are only 20 slips of paper left in that bowl. All right, and now we get to that third slip of paper. But remember, we've already taken out 2 slips of paper. So how many slips of paper are left? How many different numbers are left? Well, there are 19 different numbers to choose from. And as we go down, then when we pick the fourth paper, there are 18 different numbers left over in that bowl to choose from. And then 17 different numbers to choose from in that bowl. And then 16 different numbers to choose from. So when we select 6 different pieces of paper, the number of different combinations or possibilities that can possibly occur happen to be 21 different choices for the first, times 20 for the second, times 19 for the third, times 18, times 17, times 16. This is a huge number if we put this in our calculator. But I'm just going to leave it right there as it sits on the bottom. So our denominator for the total possibilities, whatever that is going to be, is 21 times 20 times 19 times 18 times 17 times 16. Okay? That's what we're looking at to start. Now, how many different ways are there to win? So I'm going to take my slips of paper. 1, 2, 3, 4, 5, 6. Okay? And I have a winning combination of 6 different numbers. So I'm picking 6 specific numbers that are going to be the numbers to win. Okay? Alrighty, so in my head, let's just say it's 6, 5, 4, 3, 2, 1. Those numbers, 1, 2, 3, 4, 5, 6. Okay, maybe it's 7, 8, 9, 10, 11, 12. Pick 6 other numbers. Doesn't know, but we're going to pick to win. You have to get these 6 numbers. So let's just say, just for sake of understanding, it's 6, 5, 4, 3, 2, 1. All right, well, to win, to get that winning thing to occur, how many different possible things can I choose when I select out that first paper? Well, because there are 6 different numbers that I need to win from, there's only 6 different possibilities that are going to be counted as a win, right? 6 different numbers are going to make this win up. So my first slip has to be one of those 6 numbers, okay? It has to be one of those 6 different numbers that I've chosen. So that's going to be 6 different ways I can choose that first slot and have a win going on. Now, how many numbers are left over in my winning combination? Well, if I've chosen one of those numbers, all right, now I have 5 more to match to make that win, if I'm making any sense. And so I have 5 more slips of paper that could possibly match to make my win. Keep going on, and I multiply, and the next slip of paper now has gone down, and there are 4 different ways of getting that next number. Then 3, then 2, then 1. What's happening is I have to choose 6 numbers. Okay, and there's a 6 winning combination, whatever that is. Okay, 7, 5, 4, 3, 2, 1, 1, 2, 3, 4, 5, 6, whatever that winning combination is, I set that win. Those are the numbers I have to get. So on the first slip, I have 6 different chances, 6 different numbers to choose from. But let's say you pick a 2. All right, now I have 5 more numbers left to choose from. All right, now I have 4 more numbers that I have to get to win. And then I have 3, and then I have 2, and then I have 1. Okay, that's the idea behind the number of possible wins. Let's put that in my numerator. So we have 6 times 5 times 4 times 3 times 2 times 1. Again, if we had already talked about permutations and combinations and those ideas, this would be a little simpler. But for us, this will kind of do the trick for us. Hopefully this is making sense. Now finally, we need to calculate this number. This is the probability that we will win, okay? And I'm going to do a couple cancellations. I like to reduce fractions. That's one of my favorite things to do because it makes it much easier when I go to plug it into my calculator. And I noticed that 5 times 4 is 20, so I'm just going to go ahead and cancel out those values, those factors. And I also know that 6 times 3 is 18, and 2 divides into 16 8 times. In other words, before I plug this number in my calculator, I do my math first by canceling common factors from numerator and denominator. In the numerator, I have the number 1, and in the denominator, I have 21 times 1 times 19 times 1 times 17 times 8. And if I plug this into my calculator, this is going to give me the probability of winning. Depending what calculator you use, whether you use Desmos or whether you use a scientific calculator, in any case, what you should get is that you're going to be taking 1 divided by the number 54,264, and that's going to give us the probability of winning. 1 divided by 54,264. That's what we're going to multiply by 40,000, okay? Then we have to look at the probability of losing next. Well, when I think of a probability of loss, since I already have the number or probability for winning, the probability of loss is actually going to be much simpler. Why is that? Because for this particular game, you are either going to win or you are going to lose. In other words, the probability of losing is that idea of a complement. A loss is the complement of a win. If you don't win, then you're going to lose. So in order to calculate the probability of loss, I simply have to take 1 minus the probability of winning. This is the idea of things that are direct opposites, or if we like, complements. If I don't lose, I'm going to win, or on the other way, if I don't win, I'm going to lose. So to calculate the probability of loss, I simply have to take 1 minus the probability of winning. So right here, the probability of loss is going to be 1 minus 1 over 54,264. That's going to be my probability of loss. We're so close to the finish line. Let me erase, give us some space so we can finish up these calculations. All right, so to get our expected value, the first thing we have to do is we have to take the probability of winning, which is 1 divided by 54,264, and multiply that times the win amount. So we're going to be taking on our calculators or Desmos or however you use to calculate, you're going to take 40,000 divided by 54,264. Then, after that, you're going to add to that what we have over here on this other side. Now, let me do a little bit of simplification here. Just because I'm a mathematician, and again, before I plug things into calculators, I like to do it as simple as possible. 1 minus 1 over 54,264 is the same thing as taking a common denominator, 54,264, and putting it in the denominator and the numerator, and putting those two together gives us 54,264 minus 1, or 54,263 over 54,264. I'm going to stick that number in my equation and multiply it, right? Multiply that times -1. So when I multiply this times -1, it actually gives me negative 54,263 over 54,264. What does that make our expected value? Well, notice we have the same denominator, so I can actually go one more step before I even pull out my calculator and add these two fractions up. How do we add fractions? Well, if they have the same denominator, we simply add the numerators, right? So I'll take 40,000 plus a negative 54,263, or if you like, minus 54,263. So that's going to give us negative 14,263 in the numerator, 54,264 in the denominator. We would say that this here is the expected value of this game. We like to convert it into dollars, so we're going to go ahead and rewrite this as a decimal. Take 14,263, and let's divide it by 54,264. When we make that calculation, we get negative 0.262844. And again, because it's a dollar amount that we're talking about with expected value, we're going to round to the nearest hundredth or 2 decimal places. And so the expected value for this game would be 0.26, but negative. In other words, a loss of about 26 cents for playing this game. I hope this makes sense. Again, it's a little more difficult by not having talked about specific counting principles, but I think the logic still holds true and you'll be able to follow the reasoning and arguments. And anyways, I hope this makes sense, and if you have any questions, please reach out.